So we haven't talked yet about strength of metal-ligand bonds. Thermodynamics is basically just how strong are those metal-ligand bonds. So let's start out talking about thermodynamics, or just equilibrium constant expressions. So when you're talking about an equation like this, where you have a nickel hexa-aqua-nickel complex, and you add ammonia to the reaction mixture, you get replacement of all of the waters with ammonia. Which side is favored? Or, in other words, which of the two ligands, water or ammonia, has stronger bonds to nickel? It's also just a question of which ligand is better for nickel. To talk about things like this, we use equilibrium constant expressions. When we're talking about metal complexes, we put a little F subscript for formation. So it's formation of a complex. In this case, I'm going to write the KF for formation of the hexaamine nickel. So my KF is equal to the concentration of the nickel, the hexaamine nickel. Now when I draw this in an equation, the brackets here that I draw in the equilibrium constant equation are not the same as this. So what we basically do is we drop the brackets that are in the chemical equation, and we drop the charge, and we just draw this where these brackets mean concentration. And these brackets up here mean a metal complex. Or they show you what is in the inner sphere of that metal complex. So just a notation thing. And so this is the correct equilibrium expression. I am dropping water out of the expression because it is the solvent. So you drop water because it's the solvent. You drop the charges, and the brackets mean concentration. So you essentially drop those metal complexation brackets that we have been using. This formation constant expresses the relative strength of the two ligands in this case. So it tells you the relative strength of the NH3 ligand versus the water ligand. And in this case, it means that it tells you the relative strength of ammonia in the presence of a solvent. So this is an important difference, or important point to understand. Most of these formation constants that we can find in the literature are relative to the strength of the solvent. When we're talking about KF in water, it's important to also understand that when we're using these terms, KF depends on what the solvent is, and it also depends on pH. So if you had a KF value, that KF value at pH 7 would be different than at pH 6 or pH 3. It would also be different if you switched your solvent from water to methanol. So they all depend on the solvent conditions, and that means the solvent identity and the pH. And I will warn you, there are two different types of constants. There's a K constant, and there is a B constant, or beta. And these two things are not the same. And I'm going to give you a problem to do in your next homework assignment where you're going to see how confusing this can get. Sorry. So the story is, basically, there are a bunch of different chemists around doing the experiments and publishing formation constants. Some of them were publishing formation constants in water. Some of them were publishing formation constants in methanol. They were all doing it at different pHs. And so somebody thought that maybe it would be a good idea to be able to give a constant that could be comparable across all different types of solvent conditions. And that's what beta is in the strictest definition. So this has been messed up a lot. And if you need to ever look up this information, you must go pre-1970. And Martel and Smith is the best reference to start. Just for your future, I wish my inorganic chemistry teacher had told me this So I'm telling you, don't go to the more recent papers. Hardly anybody knows what they're talking about. So the beta value, you'll see this in your textbook. It's an overall stability constant. And by most definitions, it does not depend on the solvent or the solution conditions. And I say most because it's most but not all. So what we drew up here, this was a competition between the solvent ligand and another ligand. The beta value is often written, the expression, the equilibrium expression, like the chemical equation, is written like this. So you have a metal with some charge, you add 6 ligands, and they all bind to the metal together. In this definition, usually they mean that this is the naked metal. It has no other ligands. And so this, the only situation you really have a naked metal ion is when you have organic solvents that cannot be ligands. So something like hexane, you can get that metal to get into the hexane, then you can do an experiment kind of like this, or in the gas phase. And so this is really not very representative of solution conditions at all. Your beta value here would be ml6 times the metal concentration times the ligand concentration to the 6th power. In this definition, basically you have a naked metal ion and you have 6 ligands that all bind at once. When you have a true beta value where it's not considering solvent, you have to translate it into something useful. It's because all 6 ligands can't bind at once. So what we usually talk about is the stepwise beta values. So a stepwise formation constant would be something starting with the naked metal. And I'm just going to drop the N plus here just to do some shorthand. The naked metal plus the first ligand would give you a metal ligand complex. And now this is a beta 1 value. It's the same as, and again, this is where it gets hairy. So they define this as KF1. Now, if you're not defining the solvent conditions here, then this KF1 also does not depend on the solvent. So a lot of the times people will put a prime up here. I think the confusion in the literature comes from the fact that there's only 2 letters that they use to define a whole bunch of different things. So I'm going to define this as KF prime, and this is going to be equal to ML over M times L. So this is step 1, right? And then your next, so for formation of ML2, there's 2 ways to do it. You can look at the stepwise, which would be basically this ML plus another ligand going to ML2. This is different than if you look at the overall, which would be M plus 2 L's going to ML2. Okay, so the first one I drew is a stepwise. The second one is the overall. The overall is defined as beta. So this would be beta 2, and it's equal to ML2 over M and then L squared. The first one of the ML2 formations is actually defined as your KF2, and I'm going to define it as a prime because I'm still not considering solvent here. So ML2 over ML times L. So see, these things are defined differently. It turns out that the beta 2 is equal to beta 1 times KF2. So then you could do the same thing for formation of ML3. And you could do this for all the way up to ML6, but I'm not going to go that far. So you have your stepwise, which picks up from the last stepwise, which is ML2 plus a ligand, goes to ML3, and your overall which is just the naked metal plus 3 ligands. So the beta 3 is actually equal to beta 1 times KF2 times KF3, or you can just say that it's beta 2 times KF3. And so there's like a whole bunch of equilibrium expressions that you can write for the same complex formation. So that's where some of the confusion comes from. And that's all I'll tell you for now. So it turns out also, if you're going into any kind of biochemistry field, often in the biochemistry or molecular biology, and you'll need to know this if you want to talk to biochemists or molecular biologists, they use a different form of this. They use KD values, and KD is just 1 over the KF. And instead of, if you write your formation expression, so which would be like M plus L going to ML, so KF is equal to ML over ML. In this, when you're talking about KD, it's the opposite equation. So it's the ML dissociating into its two components. So you could write this equilibrium expression basically upside down for the KD. And the reason that biochemists do this is because it's convenient for them. So it's because for protein metal complexes, you usually have 1-to-1 metal to the protein, or I'm just going to represent it as ligand. So when the total metal is equal to the metal that's free plus ML complex, the KD is equal to the concentration of ligand when 50% of the metal is bound. And they basically can just talk, that way they can talk about concentrations of ligands. So it's a convenience factor for biochemists. So the KD, yeah, it's just the opposite. It's just the upside down equation for KF, or it's the opposite. It's the dissociation constant for the dissociation reaction rather than the association reaction. We're going to use this information to talk about trends, and I'll wait till next time to start this. But we're going to look at the trends in metal stability constants. And we're going to be focusing on these stepwise constants for the rest of our arguments. And we're going to be able to understand why trends happen based on ligand field stabilization energy.